Assalamualaikum and hi. Today, we would like to share about our mini project title, which is Light at Proximity Security System. We have several contents. Number 1 is introduction, number 2 methodology, number 3 is simulation, number 4 is result, number 5 is discussion, number 6 is conclusion and recommendation, and last one is commercial potential and cost of project management. My name is Nur Shahinda binti Muhammad Zulkifli and my metric number is 222060441. Next, I will go to introduction. The Light at Proximity Security System, in the short form LAPSS, project represents a significant leap forward in security technology innovation. LAPSS designed to enhance situation awareness and response capabilities, leverage cutting-edge light-based sensor and proximity detection mechanism. Despite encountering various limitations such as scope constraints, budget limitation, technical complexity, equipment constraint, and unforeseen challenge, the LAPSS project remains poised for success. This challenge not only provides valuable learning opportunities but also foster innovation and growth without the project team. Looking ahead, LAPSS holds promise in addressing the pressing need for advanced security solutions in today's dynamic environment. By acknowledging and managing the project limitation, we can navigate the challenges effectively and make informed discussion through its life cycle. LAPSS stands as the testament to the power of collaboration, innovation, and determination in tackling complex real-world problems. With continued dedication and perseverance, LAPSS has the potential to make a meaningful impact in enhanced safety and security, paving the way for the future investment in security technology.
A very good day to everyone. My name is Pradhameshwarar A.L. Kadirvel. My matrix number is 2220604 and I'll be taking over from Inda. And without further ado, let's go into methodology. So for our project, the LAPSS, we are using 5 components. We'll be using an LED, which will be the light source to illuminate the path, a breadboard to secure all the connections to. We have an Arduino Uno, which is where we'll be doing our programming, where we will be sending our programming. An ultrasonic sensor, specifically the HCSR04 model, and a micro servo. We'll be using 2 of these. One to steer the ultrasonic sensor as a sweeping motion, and the other as the holder for the LED. So, without further ado, let's go into the code. So I've broken the code down into 3 major sections. There's 3 major sections. The first section is where we will define all of the functions. So we can see that we've defined all the pins, the servo motor, and here we have our setup where the code will only run once. This is where we will set the trigger pin, the echo pin, the LED pin, and so on and so forth. The second section is the loop function, and in this function is where we have set the motion for the first and second servo motor. So the first section here, this is for the sweeping motion. So the ultrasonic sensor is always in a 15 to 160 angle sweep. The reason why we set a 15 to 160 and not a 0 to 180 is because the ultrasonic sensor senses in a cone-like pattern, so this angle accounts for the visibility of the ultrasonic sensor. So it does not need to go all the way to a 0 degrees and all the way to 180 for it to detect objects in that range. And the second part of the function is where we will match the position of the first servo motor with the second one if an object is detected. And this is the code, the third section, the get distance. So this would be where we will be able to calculate the distance at which the object is triggered at. So this is important because if we do not have this, then obviously we wouldn't know at what level should the alarm trigger. So we have a set distance. In this case, it's 20 centimeters. Okay, now we have 2 simulations. I'll pause this first. I'll show this one. So first off is the Tinkercad simulation. As you can see, the first servo motor works as usual. It just keeps on moving. But the moment we trigger it, you can see that now both of the servos match up. So the first servo would have the ultrasonic sensor on top of it, and the second one would have the LED. Obviously, we couldn't attach it in the simulation, but that's why we have the hardware later on. But you can see that it works. So this is me trying different angles to see that it actually works. So every single time it detects an object, it will always pair up with the second servo to point the LED in that specific direction. So now we have our hardware simulation. So you can see that the ultrasonic sensor, when it detects something, so I'm using my hand. I was using my hand to just detect, to simulate an object. You can see that the LED and ultrasonic sensor are now facing the same direction. So the LED is now illuminating that specific path. So in an ideal world, rather than using a ultrasonic, no, rather than using an LED, we would be using a torchlight. So it's more focused, the light, or maybe a laser, depending on what you would need. And this is me checking out a different angle. As you can see, it still looks perfectly fine. I will do another angle somewhere around here. You can see the LED swooping. Yep, perfectly in line. So that's for the simulation. Now we have the results. So the purpose of the result is because an ultrasonic sensor can be inaccurate at times. So this is what we did. So we did an ultrasonic accuracy test. This was done on the hardware, not the simulation, because simulation is fairly accurate, right? Because it's a set online simulation. The modulus that they've been using, it's fairly accurate. So this is with the hardware, as you can see. The further away the object is, the less accurate the ultrasonic sensor will be. This is because of external factors, external interference, one of which is temperature. So if the temperature is too high or too low, then it can affect the rate at which the waves bounces back. So you can see that the graph we plotted here, which is quite accurate. So quite happy with the results that we got. But it's not quite a full-on linear line. You can see the drop here very slightly.
Next is about discussion. The ultrasonic accuracy test show that the sensor tend to overestimate distance at 10 cm, 20 cm, 30 cm, and 40 cm. Factors like calibration, environmental condition, signal reflection, and sensor limitation contribute to these discrepancies. Calibration adjustment and understanding sensor limitation are key to improving accuracy. Graphical analysis help identify trend for recalibration and optimizing condition. Factor investigation is needed for better accuracy in real-world application.
Assalamualaikum and hi. My name is Wan Ahmed Nizamuddin bin Wan Jalaluddin. My metric number is 222 060 and 4 and 77. Okay, so let's move on to conclusion and recommendation. As for conclusion, we successfully implemented a light aided proximity security system, or for short LAPSS, for enhanced security in our area. Key findings include efficient detection, real time monitoring, customizable configuration, and integration potential with existing systems. Challenges included environmental factors affecting sensors accuracy, occasional false alarms, and maintenance requirements. As for recommendation, for future enhancements, we recommend investing in advanced sensor technology to mitigate environmental impacts and reduce false alarms. Implementing redundancy measures can ensure uninterrupted surveillance, while integrating data analytics will enable intrusion patterns analysis for predictive security measures. Additionally, comprehensive training is essential for optimizing system performance and longevity. So next, last but not least, commercial potential and the cost of project management. As for commercial potential, the Light Aided Proximity Security System, or for short LAPSS, holds promise to various sectors, including residential, commercial, industrial, and public spaces. Its advanced features make it suitable for enhancing security and situational awareness in diverse environments. And next, cost of project management. The development of LAPSS incurred costs in labor, material, research, testing, and project management software. Careful considerations of these costs is essential to optimize resource allocation and maximize LAPSS's commercial viability in the security technology market. So, that's all from our group. Thank you.